So now we have contributory talks. The first talk is grade estimation of mineral resources and application of cellular automata by Soumyadeep Paty, Department of Mining Engineering, Kazi Nazrul University, Asansol, and Supreeti Kamilya, Department of Computer Science and Engineering, BIT Misra, Ranchi. This paper will be presented by Soumyadeep Paty. Soumyadeep, over to you.
Yes. Very good morning to all. Now I'm don't want to waste more times. I just like to share my screen. Yeah, I think my presentation screen is visible to everyone.
Yes.
Okay, fine. Okay. Now I'm going to deliver my talk that is on the grade estimation of the mineral resource and application of cellular automata. Actually, I am completely from mining background and I'm just starting to explore the field of cellular automata and in the application of it in mining industries. So the grade estimation, that is, I mean, a very much important part of any mining or mineral processing industry, or in case of petroleum industry also. So those are the outlines of my study. Actually, in this study, we try to estimate the grade based on some sample points. The two-dimensional cellular automata is used for the estimation purpose, and actually it is used the ordinary Krigging function. I will discuss this later on. That ordinary Krigging function as the transition function of the CA. And this method gives the result that is identical to the ordinary Krigging method, but much simpler way. Krigging is comparatively complex thing than this cellular automata model. Now, how do we get the minerals or metals from the earth crust? Actually, those are occurs in the earth crust, but what we need to do, we need to first mine it and then process it by some different way. Okay. So what is mining? In mining, we just extract the mineral from the earth crust. Either the part, I mean, the earth crust has been broken by means of blasting, or it may be extracted by means of some mechanical means, and then it is transported to the transported for the mineral processing. Okay. So there is some typical examples of the different minerals of different metals, like hematite for iron, bauxite is the ore of aluminium, chalcopyrite is the mineral of copper, and galena is the mineral of lead, which is occur in the earth crust. We just extract it from there and process it and finally get the final metal. So here one terms is there, that is ore. So what is the actually definition of the ore? Because it is very much important for the mining personals or the personals who is attached to the mineral processing. That is, actually we may get the minerals of different grade. Let's say it is represented by the weight percentage. Okay, so let's say from 0 to 100% grade we can get the minerals. Okay, theoretically. So, but it is not like that every every grade of minerals which is occurring in the earth crust that can be used for our day-to-day purpose, because if the grade is very much low, then we cannot process it economically. Okay, because of the cost of mining is there and also cost of mineral processing is there. So the problem is that if the grade is much lower, in that case we cannot process it. So to a certain grade, that grade is called the cutoff grade. Below which we cannot process it. So above the cutoff grade, the mineral which contains the grade is above cutoff grade, that is called the ore. Okay, so now the some basics of the mineral processing. So what we do actually, do we just extract the metals or some minerals or some in case of petroleum, the mineral oils from the ore or the raw material. So in case of in general process, that is first is the size reduction, then we segregate the different size particles by means of screening, And finally, some physical process like flotation or some magnetic separation is there to separate out the concentrated material. And the final process is dewatering and find out the solid or liquid, whatever it is, the final product. So that is the main part of the mineral processing. So now what is the importance of grade in case of mining or in case of mineral processing? Because if we do not, estimate the grade properly before mining or before mineral processing, then we cannot design my mining process properly, or we cannot choose the proper process for the extraction of mineral. So it is very much important to know the grade of the minerals prior to the mining or prior to the processing of the mineral. And the second point is the profit is directly depend on the mineral of the grade. It almost linearly depend. Okay, so above the cutoff grade, it is almost linearly dependent. If the grade of the mineral is increased, then the profit is also increased. Now there are some different grade estimation methods are there, like inverse distance square. All those methods are mainly interpolation method. Okay, so I'm coming to the point later on that why these methods are used. Why we can use this method, the interpolation method. So these are the some different methods which are used to estimate the grade from some sample points. Okay, like inverse distance weighting method, nearest neighborhood method, Krigging, and some copula based estimation method. So first I like to just describe that what is the block model, because it is very much important to estimate the grade by means of interpolation. So block model is one three-dimensional represent the let's say in XYZ in three direction the whole ore body space is there. I mean where the mineral has occurred, the mineral body, you can say. Ore body means the mineral body. So that is divided in equal size of three-dimensional blocks. Okay, in XYZ plane or XYZ coordinates, and each block contains a single ore value. Okay, so for a particular block, the grade value is not varies from one part to another. That is the main consideration in case of block model. Okay, so if we can find out the grade value of each block, then we can easily say that the total, how much the mineral content by the total ore body or the total block, that we can calculate. Okay. So now what is the requirement of the grade estimation? I already told you that grade, there is some importance of grade, and now I'm telling you that why it is required to estimate the grade. Because it is not possible to entirely measure each, and because in this picture you can see there are multiple blocks. I mean there are so many blocks. So by means of geological exploration or whatever the sampling technique, we cannot sample for each and every block. Okay, so what we need to do, we need to estimate it somehow. Okay, we cannot determine it before mining. It is not possible, because you cannot, you can see this in k axis, it is the height. Okay, so this part is the surface part and this is the underground. You can see if we started from the surface, then what will exactly happen here, those parts, all those parts are below the surface. Okay, so we cannot directly go there and determine for each and every block the grade. We cannot determine for each and every block. So in this particular case, we need to go for the grade estimation. So in case of grade estimation, what we will do, we will make some boreholes like here, some in some random order or some in some pattern. Okay, so we just do some boreholes and collect the borehole data. So those are the few numbers of, we can only get by means of the borehole data, we can get the very small number of blocks grade value. Okay, and by those grade values we are estimating by means of some interpolation method. Okay, so let's say the Krigging is used for estimating the grade. Now what is the spatially correlated data? That is very much important, because the data of the ores in the ore body, that is the spatially correlated. Okay, so that is the reason for which we can go with the interpolation method to estimate it. If the data are not spatially correlated, means if let's say one data is not been dependent on the data we just present beside it, then we cannot go for the estimation by means of the interpolation method. Okay, so in case of spatially correlated, what is happened? The one point, data on one point is related on the spatial location of it. And in case of known grades, by means of sampling, we find out some known grade, known grade values of few blocks. So those carries the information of the unknown blocks. Okay, that is, that is the thing, for which, that is the phenomena for which we can use the interpolation. Now, what is Krigging? Krigging is one type of interpolation method by which the grade has been estimated. So, as in this side, I show some methods like inverse distance weighting method, nearest neighborhood method. So, these are the interpolation methods. But actually, this method is very much easier method, that inverse distance weighting method or inverse distance square weighting method. But it is the deterministic method and no directional biasness is considered. But in case of Krigging, the Krigging method is uncertainty and directional biasness has been considered in case of Krigging. So that this Krigging method is widely used method in case of grade estimation. And it is the based on variogram model. So what is variogram model? So in case variogram model is one model by which we can estimate the relationship between 2 points. Okay, or 2 spatial points, 2 points which of which the data is spatially correlated. So here the gamma h is the semi-variogram and it can be determined by means of this formula. Okay, so here z of xi and z of xi plus h are the 2 grade values of xi and xi plus h. Let's just wait. Okay, let's say few points are there and those points are h distance apart from each other. In this particular place, the grade value of this is z of xi and this is of z of xi plus h. Okay, so by calculating the covariance of these particular 2 points and dividing it by the number of pairs, we can find out the variogram, and just half of this is the semi-variogram. Okay, this semi-variogram is used for Krigging purpose. So this is the modeling, the lag distance. This is the lag distance, this is h lag, and this distance, if you say 2h, then this is the 2h lag. Okay, so here we plot the variogram model as a graph, gamma h, the semi-variogram, versus the lag distance h. Okay, and there are different terminologies for this particular graph, which is important because in case of Krigging calculation and for our proposed model also. So here one is the first is the range. So what is range? Range is the particular lag distance beyond which there is no spatial relationship present, or the gamma h value will become constant after the particular point. So the variation, the dependency is only present within the range or within the A. A is considered as range. So within the range, the spatial relationship is present. Beyond the A, there is no spatial relationship. Then C naught. C naught is the nugget. Actually, it should be start from 0. Okay, the graph should be start from 0 like this way. But some nugget effect is there. Because of this, the graph is started from here. So nugget means the micro level variation, or there is some measurement error. For a particular point, let's say here I put one point. Let's say it is xi. So xi, if I say it is xi, so there is no variation for the same point, because the data is already known. So there should be no variation. So if the no variation is there, then if the lag distance is 0, then the semi-variogram also should be 0. But in the practical scenario, it is not 0. Some value is there. The some semi-variogram value is there for 0 lag distance. So that is because of either maybe for the measurement error or maybe for the micro level variations. Next is the seal. Seal is the variogram value at h range, means the highest highest value of the semi-variogram. And spatial relationship, that is the calculated value. This distance is called the spatial relationship. This distance is called the spatial relationship. This is called the spatial relationship. the difference between the seal and nugget. And the model is the spherical model, so the gamma h can be calculated by this formula. That is the formula for any spherical model. So that can be calculated for any lag distance. If it is less than a, then this is the formula, and if it is more than a, then it will be fixed at seal. So the seal value is c, so c is fixed. Now, what is Krigging? By Krigging, we can estimate the mineral. Estimate the grade of mineral for a particular point. Let's say zx0. The point on which we try to estimate our grade values. Okay, and it can be estimated by this formula where the zxi, this is the sample point data, sample point grade value. Okay, and lambda I is the weight for each data. That will be calculated. I am showing it. That is calculated from the covariance matrix. So what is the covariance matrix? So this is the covariance matrix. Okay. So gamma 11, gamma 11, gamma 12, those are the covariance for 1 to 1, 1 to 2, like 1 to n this way. Okay. And similarly 2 to 1, 2 to 1 mean we have to put the 2 to 1 lag distance and find out the gamma from this equation. The lag distance we need to put here. 1 means lag is 0, 2 means also lag is 0, and here 1 means let's say in our case the block size is 20 meter, so age is 20. Similarly for let's say gamma 13, in that case it will be 20 multiplied by 2, that is 40 meter. So by this formula, the h value we can get from those metrics, and we just put it and find out the gamma. And now those are the equations. From these metrics we can find we can formulate these equations, and we need to solve all those equations to find out this weight matrix. The Krigging weight matrix, lambda 1, lambda 2 up to lambda n. So that is the main problem of the Krigging. Okay, because it consists of n plus 1 number of solution, where n is the number of sample points. So if the number of sample point is so much, then the value of the equations is also more, and we have to we have to solve all those equations. So that is also a complex job. So that is the main complexity occur in case of Krigging. So we try to avoid by means of the cellular automata model. So here is some basics of the cellular automata. The L is the lattice, and so it is represented mainly in quadruples of L, D, L, S, M, and A. So here L is the lattice of the all cells, and in my case it is the blocks. Okay, S is the set of states, M is the neighborhood vector. So here in my study I used the moon neighborhood. So and F is the transition function. So transition function I have used, that is the Krigging estimator function. Okay, so Krigging estimator function I have used here. And now the G is the global transition function, that is from
We can't hear you.
We can't hear you. Yes, I guess we can hear you now. Please speak, Soumyadeep.
Hello.
Yes, continue.
Okay, fine. I mean, there may be some problem from my end also. I don't know. Okay. Now here we used some finite size cellular automata and that is the 2D cellular automata we used here. We actually take one slice of the blocks from 3D to 2D and then apply the 2DC on this. So for 2DC there are two neighborhoods, two types of neighborhoods are present. One is the Van Neumann neighborhood. Here only the no orthogonal grids, I mean no orthogonal cells are considered. So I am not using it actually for my study. I used the Moore neighborhood. So in this case, all 9 neighborhood dependency is there. The central cell, it depends on all the 9 cells, and here the non-orthogonal cells are additionally considered. Then the von Neumann, and this is used in my study. So now the what are the data we used in our study? The data are collected from one iron ore deposit, which is situated in the India, and the deposits spread 1160 meter south north south as well as 1020 meter east west direction, and the depth of which it is the data has been collected, that is 140 to 340 meters. So by means of borehole the data has been collected, and for the block model purpose we use 20 by 20 by 20 blocks. Okay, and CA, I already told you that CA is applied on the horizontal slice. Okay, and this is the borehole plot, which is the 71 borehole data are collected, and for those 71 borehole data this is the borehole plot. And in starting, the one spherical variogram model has been prepared from this borehole data. Okay, and this is our experimental variogram model. Okay, the black color line you can see that is this line is the experimental variogram line, and the red color line is the spherical variogram which is fitted over the experimental variogram data, and we find out the value which are required for our study, that is range, seal value, nugget, and the spatial value. Now I think I already told all those things. The transition function, you just see it, the transition function that is we used here, that is the Krigging function. Okay, for t+1 stage we use this summation of this of the t state. I mean the previous state data grade values are used for the next stage calculation, like this way. So here 1, 2, 3, the cell number is mentioned here, and actually it will run from 0 to n. Here n equals to 8, means all the blocks 1, 2, 3, and this block is considered as the 0th block. Okay, but for this particular block, the 0th block, the calculation is actually not required, because the weight matrix, the lambda I for age equal to 0, that is 0. So this calculation is not required. So we need to consider only the 8 blocks. Okay, block cell 1, 2, 3, 4, 5, 6, and 7, 8. That 8 cell we need to consider for our study. The central cell, the C0 cell, that is not required to calculate, because the transition, as per the transition function, the lambda I where age equals to 0, that is 0. So now this is the matrix by which we can calculate the lambda I value for this particular part. Okay, the same matrix, but it is reduced to 9 by 9. Okay, because only the 8 cell is present here, so we need to calculate for the only 9 by 9 matrix. Okay, and all those values are constant. Okay, all those values are constant because there is only 2 distance from here to here, here to here, here to here, and this side. These 4s are 20. These 4 are 20 meter, because
Soumyadeep, you have to wrap up in 5 minutes.
Okay, fine. Okay. So it is 20 meter. That age distance is at 20 meter for the horizontal and vertical levels, and for the diagonal levels it is √2 into 20, that is 28.28, and for the 1, 1, 1, 2 where the lag distance is 0, the lambda is also 0. So all those values are constant. So we can find out this thing that is also constant for all the equations. We need not to recalculate it again and again. Now initial configuration is for this CA is the sample data, and where is no sample data present, that is considered as 0. For the next step, if the state of the cell is changed to some values, that will be the grade value, and if it is not changed, then it will remain 0. Okay, and finally what we will do, we'll just put all the 2D slides to a 3D one. Okay, now this is our results. You can see that for the first one, that from this is our sample data. These two are our sample data, and at the stage 1, and it is the slice which is considered here, that is at the depth of 280 meters block center size, that is considered for this calculation. That is only one slice. The part of one slice is presented here. And what we will do in the next stage, we just, by means of this dotted line I am showing here, we just lock it. We will not apply our CA rule on this 9 block. We will not apply the rules. Similarly for here also, for here also. Okay. So one thing we can see that after 1, 2, 3, 4, 5, 6, after 6 or 7 blocks, the value will remain constant. That is because of the range. Okay, because one thing I already told you, that beyond range there is no relationship. So the value will be constant. So now we lock this and reapply the same rule again. And this is after second stage. Now what we will do? We just, by means of dotted line I am showing here, that part will be locked and the rule has been applied again. So this is the final grade values after 7 stage of iteration, or 7 times state change, you can say. So this is the final one. Okay, and this is the same of the Krigging estimator as well. So if we directly calculate by means of Krigging, we getting the same values which we are already getting by means of applying the cellular automata in this particular sample space. So this is the now these 2D slides are combined in a 3D one and has been plotted by means of some plotting softwares, and this is our final plotting or final 3D modeling, you can say. So now I'd like to conclude what are the conclude my study. That is the study represents cellular automata based grade estimation methods, and 2D CA is used here, and Krigging is one way of estimation all those deposits. But the problem of Krigging is we have to calculate. I mean, we have to solve a set of n+1 sets of equations. But here we can easily solve the 9 equations and for one time only, and we get the weight values, and those weight values are constant throughout our iteration. So that will not be changed, and the results are identical results we got, but here the method is much simpler than the Krigging method. And one thing I like to tell you that here we use the 2-dimensional slice. So the vertical dependency is actually ignored in this study. So in future work, the three-dimensional study can be done by means of 3-dimensional CA. So where the vertical dependency is also been considered. Okay, thank you.
Okay, thank you, Soumyadeep. Any question? I can take in 1 or 2 questions.
I have one question. Maybe I can ask one question. So,
Okay.
Soumyadeep,
Yes, sir.
you said that the number of computations actually decreases if you use CA, correct?
Yes.
Do you have any table or do you have any numbers to justify that claim?
Actually, sir, I have run it. I mean, the Krigging is also run on the same. Same sample and same block model, and our model is also run. So runtime is reduced, but no mathematical complexity has been calculated. That has been I will.
You don't need maybe mathematics. Just the number of operations you need to probably. But if the time is there, that also maybe you can show. But the other thing that I wanted to understand is, so how you said you run it for 8 time steps, correct? Or 9 time steps, something like that you said, correct?
Yes, yes, yes.
So how do you know that is the convergence?
Yes, because one thing I like to mention here, actually I am just locking I plus one cell. I mean the last locking plus one. Okay. So here the 20-meter block size is 20 meters. So this distance is 20. Okay. This size is 20. And my range here, range is, I'd like to show you, the range is 142. Okay. So after 7 or 8 iteration, that will remain constant, because beyond that, there is no dependency present. Beyond 142 meter, there is no dependency present as per this variogram model. So here our block size is 20, and each iteration I am locking 20 meters block. So after 8 iteration, that will converge automatically.
Yes. Any other question?
One simple question: what you have done in two-dimensional space, is it possible to proceed with the one-dimensional space?
Yes, sir. It may be possible, because in that case, I need to. I need to change the style of my block model. I mean, started from one and then just proceed with it, and then maybe it is possible. But actually, the thing is that two-directional biasness is there, and it is been considered in case of Krigging. So that, if we use the one-dimensional CA, then the Krigging function, the function which is used as a transition function, that function I think that needs to modify, because Krigging is for 3-dimensional space, but I already used in 2-dimensional by ignoring the 1-dimensional biasness. That has not been considered in my study, but that should be considered. So in my conclusion, I put as a future work of this, because some variation is there along the vertical direction also, that has been ignored for this particular study.
Okay, thank you, Soumyadeep. It was really commendable work, given that you are just starting working on cellular automata.
Yeah, thank you.